Excellent, Prof. May I ask some question?
Sure. Tell me.
I think the shortest path is used in GPS in our car. For example, whenever we want to use the economical mode, we use that click on that and
Sorry.
uh,
Can you speak slowly because I often lose what you're saying. Um, tell me. Tell me again,
I
slowly.
think the shortest path problem is used in GPS. Yeah, in GPS of our cars. For example, when we use
GPS is
the economical mode, yes, the GPS of our car.
wait a
When
minute. GPS is not a method for finding a shortest path. GPS is a method for finding with a very good approximation your position. Okay, and out of GPS you know more or less exactly where you are, and so that is a start. You have a goal, and so the system looks for shortest path from the goal to the start. Why? Because it's better. Because if you move out of the prescribed path, they have already done much of the work for finding always from the same start, which is actually the goal to you, because you are changing maybe because you took the wrong turn, and so they have to redo the computation, but they have quite a lot of the computation already done, okay? And
okay, Professor.
yeah,
But I think in economical mode of its economical mode, it compares the which path is more economical. I mean, the less cost.
do you
For
see?
example,
Do you see? It's exactly what is here in the theory, because the theory does not claim that you're taking the shortest. It takes the least possible sum of all those weights, and those weights might represent cost in the motorway, and it is one choice, time to travel, and it is another choice, or simply total length, which is another choice. The navigator in the car of my wife, I have not one, I have a scooter, the navigator in my wife's car gives us three possible choices, and they are these. And how can it do it? Because it has the same graph, but three different weights on the single tracks of the graph. Okay, on the single edges of the graph. And that's why it is important to have a free, broad, general theory, not restricted to geographical length. Those weights might represent many other things. They might represent danger, for instance. Okay, in a military
exactly.
situation, you have danger on one road, and it's another type of measuring something. It might be discomfort because the road might be very bad, and so on and so forth. And you can put quite a lot of different weights, and again, this is the job of the engineer. You see, you are connecting exactly to what I was saying before. The engineer must enter a mathematical model, but how to choose the model, how to prepare the model is exactly the engineer's task, to understand what to put there. If the engineer is so narrow-minded to say, no, it must be the length of the road, then he or she is a very bad engineer. Okay?
Yeah,
All
yeah,
right.
of course.
Thank you for your contribution.
Um,
Tell me.
Thank you so much, Professor. Excuse me.
Tell
Can you
me.
hear me?
Sure, I can.
Um, for example, if we have two paths to reach vertices from another vertex, I mean, which path is better? For example, you imagine that both of them is 6. Is the first one is, for example, have has two edges, while the other one is three edges. Is it important for example, finding the shortest path?
Okay, I understand what you mean, but again, this is something which you can put inside the weights you're using. Meaning, if again, I always think of what I'm using generally. I use a Sky Scanner for finding my flights. Okay, I don't want to make an advertisement to some, but this is what I and there are options, okay, to minimize the changes of aircraft. That is a possibility, but again, it all depends on how you use the model. How you use the model, okay? You might put a different weight for taking into account the fact that you are using more or less edges, okay? Which in the case of flights is actually very uncomfortable, above all if you have some luggage, if you have to go from, say if you are in Schiphol in Amsterdam, to go from one part to the other might be something of a hell, okay? And okay, so minimizing the number of edges might be an important thing. You can put it in your model, okay? And it's not that difficult because you might put then a fake edge in each vertex with a certain weight, okay? If you do like this, then you are increasing the weight each time you change your airplane, okay? So it's just a matter of using the models. The model is there and you use it in a smart way. But again, this is exactly the engineer's job to understand how to modify, to adapt the model to what you are interested in. Okay?
Thank you so much, Professor, for your kind reply.
You're the welcome. So, okay, we can go on now, but I like very much these interventions, okay, because it can clarify things and it is important. Also, the bridge between theory and application is something which I like very much. Okay. Corollary. Out of this, we can say that every non-trivial tree, trivial means just one vertex, and so 0 edges for a tree. Every non-trivial tree has at least 2 vertices of degree 1. Why? Degree of V is naturally greater than or equal to 1 for all V. Necessarily, you cannot have isolated vertices, meaning degree 0 in a tree if it is a non-trivial tree with at least 2 vertices, okay? So now what you can do is that you sum each of the degrees, and we know very well that the sum of all degrees turns out to be twice the number of edges. But we know what the number of edges is, and it is ni minus 1. So if you sum all degrees, then you get 2 ni minus 2, okay? If we had if we had that all degrees are at least 2, then we would necessarily have 2 ni, okay? But this means, since we have not 2ni, but 2ni minus 2, it means that there must be in this sum at least 2 addends which are not 2 but are 1, okay? And this is the case only for paths where you have exactly 2 of degree 1. They might be there might be many of them up to this star-shaped tree, which has the highest possible number of vertices of degree 1. But at least 2 are necessary. Why? I repeat, because if I sum all the degrees, they could not be at least 2 for each, because we would get at least 2 ni as a sum of all degrees. But since we necessarily have 2 ni, exactly 2 ni minus 2, there must be at least 2 vertices which have no more than 1, and of course no less than 1 as degree. Okay. Oh yes, but I'm sorry, I gave this proof, but it's not a proof which I asked in the, as you see here, and it's written in the program, it's not a proof I ask in the exam. There is another way of proving it, to show that the origin and terminus of the longest path in a non-trivial tree, origin and terminus both have degree 1. Now the exercises are rather difficult, okay? And I'm not going to ask you any of the following exercises in the exam. Still, I would like you to spend how much? How long? At most 10 minutes for each. Show that every tree with exactly 2 vertices of degree 1 is a path. It looks so obvious, but it is not. Again, you see that if you have a path, necessarily there are exactly 2 vertices of degree 1, and all the others have degree 2. But now you have to prove the other way round. You have a tree, so you know, 1, it is connected. 2, it has no cycles. And one more hypothesis, there are exactly 2 vertices of degree 1. Then this is a path, okay? Show that this is a path. Looks obvious, it is not, and it's not even such an easy exercise. I think it's fairly difficult, but much more difficult is the next one. First, we call center of G a vertex U such that, look, the maximum distance from that vertex U to all to each of the other vertices is as small as possible. Okay, already this notion is a little bit tricky, but then the exercise, which is really difficult, is show that a tree has either exactly 1 center or 2 centers which are adjacent, meaning 2 ends of the same edge. Okay? It is nice, but I think it is difficult. At least for me, it was difficult. Surely there are people for which it is not. But it's not my case. Cut edges and bonds. We are starting here something, cut edge and later cut vertices, which will be the main actors in the chapter connectivity, okay? But let's start looking at what it means. A cut edge of G is an edge E such that omega of G minus E is greater than omega of G. Sorry if I repeat, but do not write this if you do not remember what omega is. So, I prefer that you tell me something which is not completely correct. Many tell me a cut edge is an edge such that its deletion makes the graph disconnected. It's not exactly true, because the graph might already be disconnected. Okay? And what we want is an edge whose deletion makes the disconnectedness greater. How to say that? By saying that the number of components of G minus E is strictly greater than the number of components of G. Example. If I have and all of this is graph G, then this is a cut edge. And it does not disconnect the graph, because the graph is already disconnected. We have in G already two components. This is one component, this is another component. What happens is that if I take away E out of this graph, then the number of components increases. 1, 2, and 3 instead of 1 and 2. So this is the correct definition. But please do not try to remember these symbols if you do not know what these symbols are. I have, unfortunately, many examples of people to which I asked, what is a cut edge? An edge is, of G is an edge such that omega G of minus E is greater than omega of G. Okay, what is omega of G? I don't know. I'm sorry, you know, I know that you laugh, but there are many people in this situation. Please do not do like this. I don't remember. I prefer something almost true as the thing I said before, or the description whose deletion makes the number of components increase. Okay, but don't tell me this if you do not know that omega is the number of components, and if you do not know what a component is. Do you remember? I stayed quite a long time on the notion of components, and I was very happy that here and mostly from outside there were questions about connectedness and the notion of component. That was a very good thing. But it is a rather simple and intuitive notion, but it must be well understood in mathematical terms. Okay? So don't fly over these things, even if they are so intuitive. Mathematical methods. Okay? So, theorem with no proof. For me, the proof is there, but I don't give it to you, and of course I don't ask it. An edge E of G is a cut edge of G if and only if, so very good, a double implication, if and only if E is contained in no cycle of G, okay? Again, the one way of the one implication is very easy, the other is not so easy, okay? Here we have some cut edges. Also, this is a cut edge a bit particular because if you delete it, one of the component left by the deletion is built by just one vertex, but still it is a component when you delete this edge, okay? So these are the cut edges of this graph. Another theorem, a connected graph is a tree if and only if every edge is a cut edge. Okay? Again, no proof, and again, it's something which is very intuitive. Okay? And now to a notion which is rather important also for applications. A spanning tree of G is a spanning subgraph of G that is a tree. I'm sorry, I think I did not give you in the previous chapter the notion of spanning subgraph. or maybe yes, but very, very quickly. If I have a graph G, I say that H is a spanning subgraph of G if the subgraph of G and the set of vertices of H is the same as the set of vertices of G, meaning that you have maybe less edges, but exactly the same set of vertices of G. So a spanning tree of G is a tree made of edges of G, which reaches all vertices of G. We have that every connected graph contains a spanning tree. And here is a proof. It is very, very intuitive. You can go and break all cycles that you have in your connected graph by making sure that you left a connected subgraph, and what you get at the end is that you get a spanning tree. Out of this, you get that if G is connected, then the number of edges is greater than or equal to ni minus 1. Why? Because the given graph contains a spanning tree, and necessarily a spanning tree has exactly ni minus 1 edges, because it is a tree and it contains all vertices of G. But maybe G has some more edges that we took away in order to get that particular spanning tree, okay? And so epsilon is greater than or equal to ni minus 1. And the proof is very easy. Let G be connected, then it contains a spanning tree, so the number of edges of G is greater than or equal to the number of edges of the spanning tree, which is necessarily number of vertices of the spanning tree minus 1, but the vertices of the spanning tree are the same as the vertices of G, and so ni of G minus 1. And here is an example of a spanning tree. Another point in my exams, I give you a graph and I ask, please give me a spanning tree. And again, many have failed just by this fact. Okay? So I'm telling you, please make a note, all of you, even the very good ones, make a note of these questions, which I'm going to ask you in the exam, because I've asked them many, many times, and I've seen that many, many times the answer was not really understood. And it is very important for me, that you know what you are talking about. Since there is a very interesting procedure and a very interesting thing now, after this, which is counting the number of spanning trees in a graph, which has a wonderful procedure, everybody learns that procedure. Why? Because that procedure is one of the things you have to do in the midterm test. Okay, so everyone is able to do what we are going to see and get a number. And then I ask, what is this number? And they don't know what to say. Well, it's 8. 8 what? What do you mean 8 what? 8 what? You are counting. 8 spanning trees. Please come next time. Okay? Okay. And what is a spanning tree? You should at least show me one. But first you give me the definition. Then I ask you, give me an example. Not that I ask you what is a spanning tree and you give me an example. First you give me the definition. Then I ask you for an example. We have also this thing which is important. It is important for a very last chapter which I'll not be able to reach. And so, okay, I never asked for the meaning of bond. Anyway, it is in what I've written as a program, and so I say it. Okay. Take subsets of the vertex set, S and S prime, okay? We denote in this way, and this will be used fairly often in the following lectures. square bracket S, comma, S prime, square bracket. What does that mean? The set of edges which have one end in S and the other end in S prime. Okay? An edge cut of G. Here, before we have seen a cut edge. Don't get confused. A cut edge is a single edge which makes that and that. An edge cut of G is a subset of E of the form S bar, where S is a non-empty proper subset of V. What does that mean? Non-empty, there is at least one vertex of V. Proper means there are not all vertices of V, some are missing. And S bar is V minus S. So there are some vertices, but not all in S, and all the other vertices are in what is said, called S bar. So an edge cut is a subset of E in this form. We have also a minimal non-empty edge cut, and such a minimal non-empty edge cut is called a bond. Okay? Each cut edge E gives rise to a bond, the set containing only E. If G is connected, then a bond B of G is a minimal subset of E such that G minus B is disconnected. Note that here the hypothesis is that G itself is connected. And here in figure 2.4, we can see an edge cut which is not a bond and an edge cut which is a bond. Here, the thickened edges are edges of an edge cut. Why? Because we can take S as this set of vertices, S bar necessarily is this other set of vertices, and actually the thickened edges are all the edges connecting one vertex of S to one vertex of S bar. Okay? Look at this other, the graph is exactly the same, but here we have a subset of thickened edges. These thickened edges are, again, some of these thickened edges. So this set of thickened edges is a proper subset of this set of thickened edges. But it is itself an edge cut. How come? It's not connecting the same sets of vertices. Yes, the set change. Here we have that S is built by this, and also this vertex. Okay, and S bar is given by these three. And actually what you have is that these edges are all edges connecting vertices of this S with vertices of this which is S bar. Okay? And so, since this is also minimal, meaning if you take away any of these edges, then you have something which is no more an edge cut. This is a minimal edge cut, and so it is called a bond. But, I repeat, okay, sometimes I want to give honors, 30 e lode, 30 and with honors, and so I might also ask for what a bond is. Okay, so, but generally I do not ask about this, okay? Because I'm not able to reach that particular, very important, very nice chapter. I've not even listed it anymore in my program page. It is the chapter on flows in networks. And for optimization, very important for engineers. But first, it is important for engineers to understand what a definition is, what a necessary and sufficient condition is, and so on. So I prefer to stay with the shorter program. But for that chapter, a bond is very important. See how much I take away. Now there is the notion of cut vertex. Cut vertex should be more or less the same. It is not because of a single nasty thing that you might have loops. And so if you have loops, you cannot give the definition which you would like to give. The definition which you would and I would like to give is this, exactly similar to the one of cut edge. In that case, an edge whose deletion would increase the number of components, and you would like it to be this, a vertex whose deletion increases the number of components. And it is so if in your graph you do not have loops. But since you might have loops, we necessarily have a much more cumbersome definition, which is this. We call a vertex V a cut vertex. In this case, if you can partition E, the set of edges, into two non-empty subsets, E1 and E2, such that the graph induced by E1, meaning the graph having E1 as edges and all their vertices as vertices, and G of E2, same thing for the set of edges E2, have just the vertex V in common. This cumbersome definition is the general one. But if you do not have, and if you already know that your graph is simple, for instance, or at least that you do not have loops, you can adopt this simpler definition. Okay? And look what's that about. This we want to be considered a cut vertex. Oh, okay, let's start with a normal one. This is a cut vertex. What happens if I delete it? Okay, we have one, we start with a connected graph, so one component. We delete this vertex and all adjacent incident edges, then we get one component here, one component here. So the number of components increases, okay? And what the definition says? It says, can you divide the set of edges into two sets of edges E1 and E2, such that if you take the subgraph generated by one and the subgraph generated by the other set, the only vertex which is in common is that? Yeah, sure. One set of edges is this, 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 this. The other set of edges is this, 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 and this. If I take the two subgraphs generated by these, one subgraph is this, the other subgraph is this, and what do they have in common? Exactly this vertex. Okay. Why this cumbersome definition? Because of this. Why? Because if you delete it, you have to also delete the loop, and the number of components does not increase. Still, you want this vertex to be considered a cut vertex. And so you must use that definition. In this case, E1 is just built by this single edge. E2 is all other edges. So the graph induced by E1 is this. The graph induced by all other edges is this, apart from the loop. What do they have in common? This vertex. So this is a cut vertex in the sense of the general definition. It would not be if you take the sort of easier definition, which is not general enough. Okay? But I will not reject you if you give me this definition. I'll say, not exactly, you know, but okay, let's go on. All right. Okay. Theorem, no proof. a vertex V of a tree is a cut vertex of G if and only if its degree is greater than 1. Okay? Good to know. We are talking about trees, so information about a tree. Oh, here there is a fact, it's strange. I was also misled by this title because I thought that Cayley's formula is the formula of this recursive procedure. And also in my first midterms, I wrote wrongly, use Cayley's formula to find the number of spanning trees. No, no. The formula we are going to talk about is has no name, I know. The formula by Cayley is just this: for the number of spanning trees of the complete graph on n vertices, and it is n raised to n minus 2. This is actually Cayley's formula, okay? But forget about it. The thing I'm fond of is the recursive calculation I shall show you now. Oh, I had to do something, okay, with dice graphs. That's nice. I was forgetting that. Let me look. Ooh. Let me see what we have after that. Connected problem. Well, okay. Let's try to finish this chapter. What we are going to see now is totally non-trivial. Okay, forget about this name of Cayley. Now we want to find the number of different spanning trees that you have inside a given graph. Okay? Of course, if you have a tree, the number of spanning trees is 1, the tree itself. Okay? Now we want to see how we can find this number. This number increases rather rapidly with the number of vertices, but it depends not so much on the number of vertices, but on the number of cycles you have in the graph. For instance, you might have a tree with 1,000 vertices, it just has one spanning tree itself. Okay? First of all, we talk about two manipulations that we can do on a graph by using in two different ways a particular edge, arbitrarily chosen edge of that graph. Pick up an edge and we might, very easy, delete it. We have already done it before, okay? So you might get a graph which is called G minus E. Already we know that. But another important operation is one which is very intuitive graphically. You can contract that edge. You think of shrinking it to just one vertex, okay? Technically, how is it? You delete the edge and identify, glue together the two ends of that edge. Okay? An edge which is a link, otherwise you cannot do it. The graph you get out of this operation, contracting, shrinking an edge to a single point, is written like this. G dot E, not in the modern notation, but let's stick to the notation of this book, okay? So G dot E means you shrink E to a point. G minus E simply means you delete E from the graph, okay? What do we know? Of course, that if we shrink an edge to a vertex, the number of vertices decreases by 1. They were 2, now they are 1. Okay, we are talking about a link, I insist. The number of edges is also the previous number of edges minus 1. Okay, because there was that edge, now it is there no more. This is important. The number of components is the same because you have not split or glued together, split a component into two by shrinking an edge, nor have you put together two components which are separated. The two vertices were already connected by that edge, you just shrink it. So these are important in what we are going to see. This number of spanning trees of a certain graph G is called by this, which is Greek letter tau. The modern Greeks call it taf, and the Americans call it tau. Okay, so tau. The book is American. I'll play the American myself, so I'll call it tau, and it is the ancestor of Latin T letter. Okay, okay. Here is this wonderful theorem. I love it. If E is a link of G, then tau of G, the number of spanning trees of G, can be obtained as the sum of tau of two different graphs. Tau of the graph in which you have just deleted E, plus tau of the graph in which you have contracted E. Okay? And here I want you to have a look at the proof. The proof has a little dirty trick. Okay, okay. I'll just show you when they play the dirty trick. Okay. Let's see what's the idea of this. The idea is this. Take the spanning trees of G, all the spanning trees of G. You put them into two classes according to what? That spanning tree contains E, or that particular spanning tree does not contain E. Okay? In this way, you can separate into two disjoint sets of spanning trees. All right? Okay. Now look at the spanning trees not containing E. They are trees, they cover all vertices, and they are, of course, also spanning trees then of G minus E, since they do not contain E. Are they trees? Yes. Are they subgraph of G minus E? Sure. They do not contain E. Do they reach all vertices of G minus E? Sure, it's the same set of vertices of G itself. So they are exactly the spanning trees of G minus E. Conversely, T of tau of G minus E is the number of spanning trees of G that do not contain E. Now, consider the spanning trees which do contain E. Okay? To each of them, there corresponds a spanning tree T contracted on E, on the same edge, of G contracted on E. And here is the dirty trick. This adverb clearly should never appear in a mathematical textbook. But the authors were young, okay? And when they are young, they can say such a thing. I want to see in the new version whether they write clearly, but it's not clear. It is true, but it is not that clear. This correspondence is a bijection, okay? And then what you have is that tau of G contracted on E is precisely the number of spanning trees. It is the same number of spanning trees of G that contain E. And then this rule follows. Okay, let's look at how we can use this relation. It is a very good relation because what happens is that in both cases, you get less edges you have that the number of edges decreases, okay? And so at the end, you have maybe a lot of pieces, but all of which have very little or no edges, okay? Where you can just count what is happening, okay? So, first thing, I show you, let me look at the time, I'll show you an example of calculation, okay? Then I wish to show you, for this particular graph, the ratio of the proof itself, okay? And then I want to give you some tricks, okay? So let's see. We never write tau of, but it should be tau of this is equal to tau of this plus tau of this, which is tau of this, and so on and so forth, okay? So here what they do is to choose this as E. And so on one side they delete it, on the other side they contract it to a vertex. Okay? Now they go on. Let's take this and use this edge as E. So on one side we delete it, on the other side we contract it. This edge becomes just this vertex. So tau of this square is the sum of tau of this plus tau of this. Take this. We can do the same thing here, taking one of these two multiple edges. Say this, we take E as this edge. Okay, so on one side we delete it, on the other side we contract it. And so here it draws its vertex, and this parallel, this other multiple edge becomes a loop here. Okay, just think of shrinking this edge, then this vertex comes here, and this edge connecting two different vertices ends by connecting a vertex to itself, so it becomes a loop. And now we go on, but stop it here. This is already a tree, so you don't have to do anything more, okay? So this is already a tree, you keep it as a tree, and you'll count it at the very end. What about this? Here we can use the recursion again. We choose this as E, and on one side we delete it, on the other side we contract it. We did not have any multiple edges here, but now we have, because these two edges were connecting this vertex to two different vertices, but when we contract this, they become the same vertex. And so out of this and this, we get two multiple edges. Okay? Here, we can pick up this as E. On one side, we delete it. On the other side, we contract it. And so we get a loop here. Okay? And here, we can pick up this as E. On one side, we delete it. On the other side, we contract it. Okay? Now, later I'll show you how to make this computation shorter. Okay? But they want to show you up to the end just the use of the pure rule they have. So, is this a tree? Yes. So leave it as it is. Is this a tree? No. So let's use once again the rule. Pick up this as E. On one side you delete it, on the other side you contract it. Okay? Now, what do you do when you have a loop? For getting a tree out of it, you just delete the loop. Forget about the loop. Leave the vertex there, but delete the edge, which is a loop. Okay? So this is already a tree. This is already a tree. this is already a tree. This is not a tree, but forget about the loop and you get a tree, a trivial tree. This is already a tree. This is almost a tree because you just have to forget the loop. And here you forget this loop, forget these two loops. And so 1, 2, 3, 4, 5, 6, 7, 8, and you get 8. 8 what? 8 spanning trees in the original graph. Okay? I want you to know that when you reach this 8, you are counting something. And this something is the number of spanning trees contained in this graph. Okay? Everybody, sooner or later, is capable of repeating this procedure. Not everybody is able to understand what he or she is doing. I want the latter more than the former. Okay, now let me show you exactly on this what I was saying, the idea of the proof. By taking this edge as E. This is a bit difficult for the use of this whiteboard. Okay, let's try. So I have my let me also give names to these edges, okay? This is already called E. Oh, how ugly. This is A, this is B, C, and D. Okay. Now, this is the edge we are interested in. Okay, so now I look for all possible spanning trees, okay? And we'll put the ones containing E on the right, and the ones not containing E on the left. Okay, not containing E, it's fairly easy. Why? Because these you get a very simple cycle of 4, and so to get a spanning tree, you just take away one edge each time, okay? And so, sorry, this D is horrible. See? Oh, okay. That edge is called the D. I'm sorry. Okay. So it's very easy to write the 4 spanning trees of this graph not containing E. One is without A, B, C, and D. One is without B, one is without C, and one is without D. Are they spanning trees of our graph G? Sure. Are they trees connected and acyclic? Do they contain all vertices of G? Sure thing. Okay? All right. Now, we have to build the ones containing E. So E is necessary. We can put there A. Okay? And we cannot put there B then, okay, because we would close the cycle. But we can put there C. Okay? Then we can have E is compulsory now. We can again have here A, and we can put D. Okay? All right, no more A. We still have E, of course, and now we can put B. But necessarily I cannot put A, as I said. I can put D, and I cannot put C, or, sorry, this was B. I again can put B, and I can put C. Oh, mind, we are not considering, we are not identifying isomorphic graphs. Do you remember when we listed all isomorphism types of graphs with 4 vertices? It's not what we are doing. This is why I wanted to put names to the edges. This is really isomorphic to this, but it is not equal because the edges are not the same. I know that they are isomorphic. This is isomorphic to this, and this is isomorphic to this, but we are counting different, even if isomorphic subgraph, in this case, spanning trees, okay? So now we have all possible spanning trees. These are necessarily spanning trees also of G minus E. Now what we do is to shrink in each of these spanning trees. We shrink the edge E, and then we can I'll write. So here I have G minus E. And here what do? I have, let me do like this, okay. Here I have that I shrinked E, and here I have EA, here I have B, here I have C, and here I have D. Okay, and this is G contracted on E. So now if I do the same thing to these, what do I get? I get A, C. I get A, or maybe you prefer that I use the same curved things I have there, okay? I do it. So I have here A and C. A and D. Here I have D and B. And here I have C and B, which are rather clearly the four spanning trees of this one. okay? All right, and this is what they say in the sort of proof. Clearly, there is a bijection, meaning that these correspond, these correspond, these correspond. So while these are actually directly the spanning trees of G man C, these cannot be the spanning trees of G contracted on E, but each corresponds to one, and this correspondence is a bijection. And so this number is equal to this number, and actually at the end you get the total number. This is the idea. Okay? Now time for tricks. Okay? I give you tricks for doing this calculation quickly, more quickly. One. If G has a cut vertex V, which, let me say, separates subgraphs G1 and G2, then tau of G equals tau of G1 times tau of G2. Example, I take such a graph. Okay, and this vertex V is a cut vertex which separates on one side G1 and on the other side, say, G2. Now, whenever you build a spanning tree of G1, you can use it for having how many spanning trees? As many as you can have on the other side, okay? And so, here you have tau of G1, which is clearly 4, tau of G2, which is clearly 3. I hope that you can see that.
Never say clearly.
Pardon me? Oh, you're right. You caught me, you caught me. I said clearly. I'm sorry. Thank you very much. I like that very much. Okay, let's pick up just this cycle, okay? Then, being a cycle, I get a spanning tree just by deleting one by one its edges. And so, not clearly, but now rather easily, we get that I get, if I just pick up G1 by itself, I get 1 by deleting this, 1 by deleting this, and leaving the others. 1 by deleting this and leaving the others, 1 by deleting this and leaving the others, 1 by deleting this and leaving the others. So a cycle of 4 different spanning trees. A cycle of 3 different spanning trees. But for each spanning tree here, I have 3 spanning trees here. Okay, let's pick up this on the left. On the left, I pick up this. Okay. Then on the right, I can have 3 different. So out of this, I get what? I get this, Sorry, this is 1, this is 2, and this is 3, okay? And so for each of the spanning tree on the left, since this vertex is a cut vertex, you have for each of the spanning trees on the left, you have 3 spanning trees on the right, which build 3 different spanning trees. Now I change this one on the left and repeat these 3 on the right. And so I get 4 times 3. In all, I get 12 different spanning trees, okay? And this is an important trick. Second trick, if G is disconnected, then tau of G equals 0. Because you cannot have a spanning tree of a disconnected thing. Okay, so, and you find this if you forget that when you meet a tree, you can stop. Assume I have this, say, okay, and I forget that I could stop already, and I pick up this edge E, and I do what? I divide into. I delete, and I contract. Okay. Yes, but of course it works because this is counts for 1, but this counts for 0 because here you cannot have a spanning tree of this graph. Why? Because this is an isolated vertex, and so no tree can reach it. Okay, so if G is disconnected, then tau of G equals 0. Okay. And also what? If you have multiple edges, particular case of 1. Okay, then what do I have? I have here necessarily 3. When I have let's do it. Let's do it as two separate things. Let's say 3. If G is a cycle of K vertices and edges, K edges, tau of G equals K, you get a spanning tree by deleting one and each of the edges. and let's say 4 if G is given by 2 vertices with K multiple edges between them, then tau of G equals K each one of the multiple edges gives a spanning tree. So, particular case of 1. Okay, so here I have 3 because of the fourth trick. Here I have 2, and so I have 3 by 2, 6 spanning trees. Okay, easy to see. Okay. All right. In far enough chapter, vertex coloring, we'll have a very interesting thing which is called the chromatic polynomial, and we'll have a similar but a bit different, similar recursive computation. There the tricks are extremely different. Don't confuse them. So these tricks are valid because of the meaning of spanning tree. Okay, there will be different tricks because of the meaning that we'll have of chromatic polynomial, which is different. So different tricks, but here these tricks hold. Okay, that's all for today. See you next Monday. Ciao.
Right. Thank you.
Bye.
Thank you. See you. Bye.
See you.